This video is about rational functions. There's going to be a lot of information in this video, and then in our next video, we'll do some examples of applying this information. So if you already have a good idea of what we're talking about here, you might want to try those videos first. You might not need to watch all of this one. Either way, let's get started. A rational function, and the word rational includes the word ratio, which we know means fraction or rate. And so a rational function is a function which is a fraction, but more specifically with an x in the denominator. That's what makes it a rational function. 1 over x is what we call the parent function. Parent function is y equals 1 over x. That is the parent for rational functions. It has a name too, by the way. It's called the reciprocal function. Now, just like with other functions we've seen throughout the year, the first thing we talk about is what x can and can't be. Now, for most of the functions we've had this year, x could be anything, but not here. There's what we call a domain restriction, which this is just a side note here. A domain restriction is something that cannot be, that cannot go into the function. That's what we call a domain restriction. And in this case, the domain restriction, and this is something you know about fractions, you cannot divide by 0. So the domain restriction is any 0 of the denominator. For example, if the function is 1 over x minus 2, actually I'm going to do this in a different way. I'm going to say 1 over 2 minus x, then the domain restriction is that x cannot be equal to 2, because that is the 0 of the denominator. That's what we call a domain restriction. We're going to have domain restrictions every single time we talk about a rational anything this unit. Domain restrictions dominate this unit. They're everywhere. They should always be the first thing you think about. Okay. I'm going to set aside the next thing on the screen, the 0, X-Intercept. We'll come back to that. But what I want to do is build off of this idea of a domain restriction and talk about something called a vertical asymptote. Let's see what happens. We just had the function f of x equals 1 over 2 minus x. So we said x cannot equal 2. So if I try to make a table of values and make a graph to go with it, if I try to make x equal to 2, I'm going to have a problem. I know that 2 minus x, which is not my function, but it's helpful, is equal to 0, which means 1 over 2 minus x, which is my function, that is undefined. That's why there's a domain restriction, because if I try to plug in 2, I don't get an answer. What happens when I try to plug in numbers close to 2, not quite 2, like 1? Well, 2 minus 1 is 1, and then put that in the denominator, 1 over 1 is 1. Hey, that's no problem. So 1, 1, there we go. I've got a point. Let's get closer to 2 even. I can get closer than 1. I can go to 1.5. 2 minus 1.5 is a half, and 1 over a half is 2. Okay, so here's x equals 2. So when x is 1.5, the y value is 2. What about when x is even closer to 2, 1.9 or 1.99? What's going to happen the closer I get to 2 is that 2 minus x is going to get really close to 0. See how that number, that 2 minus x, which is going to go in the denominator, that keeps getting smaller. And every time I divide by a smaller number, I get a bigger answer. Which makes sense. You know that if you've got a big pile of cookies to share, the fewer people you have to share with, the more cookies you get. Dividing by a smaller number gives you a bigger answer. So what happens is, as my x gets closer and closer and closer to 2, I'm going to have this imaginary fence here. As x gets closer and closer to 2, my y value is just going to keep going up and up and up and up. But it's going to happen, it's going to go infinitely big right here. It's almost like an electric fence that you just can't touch. You try to find a way around it, but it never ends. So you keep having to go up, 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 and get away from it. That's what we call a vertical asymptote. Quick note that it happens on the other side too. When x is 3, the denominator is -1, and so the fraction is down here. And as we get closer and closer and closer to 2 on this side, 2.5, 2.1, 2.01, this denominator is going to get smaller and smaller and smaller, which means the negative answer is going to get bigger and bigger and bigger. And so I'm going to have sort of the opposite thing happening on this side, where we have this electric fence going all the way down there forever, and I'm going to try and get around that fence by getting smaller and smaller and smaller and smaller, but it's just never going to be enough. And that's what we call a vertical asymptote. If we go back to the slide before, the vertical asymptote is, if you want a sort of definition for it, it is a vertical line that a function approaches. And the way you're going to find that vertical asymptote, and very important, this is not part of the definition of vertical asymptote, these are just directions for how to find it. But to find the vertical asymptote, it's the same thing as the domain restriction. You find the zeros of the denominator. Those are your vertical asymptote, or asymptotes, depending on how many there are. And then this is a really important piece here. What I want you to be able to do with this is to make a description, give a sentence here. So I want us to be able to describe what's happening at this vertical asymptote. So I'm going to give you a sentence, and you're going to pause and just recognize it for a second. What does it sound like? At a vertical asymptote, as x approaches whatever that vertical asymptote is, in our example it was 2. Of course, it doesn't have to always be 2. So I'm just going to say VA to stand for vertical asymptote, whatever number it is in that problem. So as x is approaching that vertical asymptote, f of x is going to approach either infinity or negative infinity. Now I want to make it clear that although this sounds a lot like end behavior, it is not end behavior. That is something different. End behavior, remember, happens all the way on the edges. And what we're talking about is kind of happening here in the middle of the graph. If we want to talk about what's happening with end behavior, well, that's another issue. And now's the perfect time to talk about it. End behavior is what happens all the way on the right as x gets really, really big. So imagine x being really, really big, like 100 or 1,000 or 1,000,000. What's going to happen to the denominator is it's going to get really, really big too, although negative. 2 minus 100, 2 minus 1,000, 2 minus 1,000,000. Really, really big negative numbers. But remember where those big negative numbers are going. They're going into the denominator. And what happens when you divide by a big number? You get a small answer. So what's going to happen is you're going to keep getting smaller and smaller and smaller results to your fraction. These are all approximations, but 1 over negative 98 is about the same thing as 1 over 100. It's just an approximation. I know it's off by a little bit. 1 over negative 998 is about the same thing as 1 over 1,000. Negative 1 over negative 999,998 is about the same thing as negative 1,000,000th. Off by a tiny little bit, but close enough. And so what's going to happen is as x gets bigger, you see these decimals, they're negative, but they're getting closer and closer and closer to 0. Never going to quite make it to 0, but going to keep getting closer and closer and closer. And on the other side, you can guess what would happen on the other side. 2 minus negative a million is just a little bit more than a million. And so 1 over a million is about a millionth. So again, we're going to keep getting closer and closer and closer to 0, but on this side, everything's going to be just a little bit positive. That line, this green dotted line right here, also on this side, is on the one hand, it's the end behavior. It's what the graph is getting closer to as x gets bigger. But there's another name for that, special to this lesson. It's called a horizontal asymptote. So a horizontal asymptote. To give you a definition, it's going to sound a little bit similar to what we just said. This shouldn't shock you. A horizontal asymptote is a horizontal line that a function approaches. And the sentence that goes with it is going to sound an awful lot like the sentence we just said for a vertical asymptote. But remember, the horizontal asymptote is happening over here on the edges, here and here, as opposed to in the middle with the vertical asymptote. So the sentence is going to be describing what happens on the edges as x approaches infinity. So x is what's getting bigger and bigger and bigger and bigger, and it's f of x that is approaching whatever the horizontal asymptote is. In our case, it happened to be 0. You'll see in a minute it's not always 0. Unlike the vertical asymptote, we're going to describe this in 2 sentences, one describing what's happening on the left, the other describing what's happening on the right. And you can rest assured most of the time this unit, probably 98% of the time this unit, your graph is going to have the same horizontal asymptote on both sides. It's very, very, very strange for it not to, so don't worry about that right now. Calculating the horizontal asymptote is a little bit trickier than the vertical asymptote. We already have the directions for finding the vertical asymptote. It is the zeros of the denominator. Finding the horizontal asymptote is a little bit trickier because there are 2 possibilities. So possibility number 1, if the denominator is stronger than the numerator. And when I say stronger, what I mean by that is its degree is higher. So the denominator has a higher degree than the numerator, like 1 over x, where the denominator is linear, x to the first, but the numerator is constant, which is like x to the 0. Or if the numerator was linear and the denominator was bigger than linear, quadratic or cubic, something like that. These are examples of the denominator is stronger than the numerator. In all of these examples, the horizontal asymptote is super simple. It is just y equals 0. I do want you to notice that when I write the horizontal asymptote, I will never say the horizontal asymptote is 0. Because the horizontal asymptote is a line, which means we write it as an equation, y equals 0. Just like when we learned about axis of symmetry, same thing. The axis of symmetry was a line, so it was always x equals. Same thing here with the horizontal asymptote. Okay. Second possibility, if instead of the denominator being stronger than the numerator, if the denominator is the same strength, or is, I'm going to say, the same degree, because that's what I mean by strength, the degree of the polynomial. Same degree as the numerator. For example, if we had x plus 5 over x minus 3, or x squared plus 2 over x squared minus 3x plus 5. These are examples where the degrees are the same, quadratic over quadratic, linear over linear. In these cases, it's a little bit more complicated to say, to explain, but it's not complicated to do, I promise. The horizontal asymptote in these cases is that y equals the ratio, so it's going to be a fraction, of the lead coefficient divided by the lead coefficient. That's it. So in this case, since it's 1x over 1x, the horizontal asymptote would be y equals 1 over 1. Just to make it more interesting, I'm going to pretend that this was 3x squared plus 2 over, let's say, 7x squared minus 3x plus 5. And so for this one, the horizontal asymptote would be that y equals the ratio of the lead coefficient from the numerator over the lead coefficient from the denominator, 3 over 7. That's it. Like I said, it's a little bit hard to explain and describe, but it's actually very easy to do. Okay, so we've got a lot so far. We have described the vertical asymptote and the horizontal asymptote. I'm going to go back and describe one more piece of the rational function that you always have to look at, and that is the X-intercept. We learned a lot about X-intercepts and zeros last unit. That was pretty much the point of the whole unit. This unit is not very different. The only thing is, for this unit, if I want to find the X-intercept, which remember is another way of saying the zero of a rational function, all I need to know is the X-intercept, or the zero, of the numerator. That's a big deal. It makes a lot of sense. If you have a fraction, so if you think of a fraction as some number divided by some other number, I don't really care what this number is. If this number is 0, then the whole fraction is equal to 0. 0 divided by 1, 0 divided by 2, 0 divided by pi plus e to the third. They're all equal to 0. So as long as the numerator equals 0, the whole fraction will equal 0. That's how you find the X-intercept of a rational function. So notice we're finding the zeros of both the numerator and the denominator. We use the zeros of the denominator to find the domain restriction, and that'll give us the vertical asymptote. We find the zeros of the numerator to find the X-intercept. So we do them both. With one tiny little catch, and this is the last thing I'm going to include in this video, one tiny little catch is if the 0 of the numerator and the 0 of the denominator are the same thing, which means some factor of the numerator and the denominator cancel out. Because we know that if there's, say, an x minus 2 in the numerator and an x minus 2 in the denominator, they would cancel out. So let's say we had x minus 3 times x plus 2 over x minus 5 over x plus 2. Because in both of these, both the numerator and the denominator have a factor of x plus 2, they would cancel out. We would be able to simplify this fraction to x minus 3 over x minus 5. Now, the domain restriction doesn't go away. We still would have to say x does not equal to negative 2. But because we canceled it out, it is neither going to give us a vertical asymptote or an X-intercept. The 0 of the denominator that gets canceled out doesn't leave a vertical asymptote. The 0 of the numerator that gets canceled out doesn't give us an X-intercept. If the factor do cancel out, we are left with what's called a hole. And to show you what I mean, I'll turn to Desmos. And it's a little bit tricky on Desmos. So the function we were graphing was x minus 3 times x plus 2 over x minus 5 times x plus 2. And according to the x plus 2's, we would expect to see a vertical asymptote at -2, x equals -2. But it's not there. Or, according to the 0 of the numerator, we'd expect to see a X-intercept at x equals -2. But it's not there. What is there at -2, though? So in order to do that, let's take a look and see what's happening in the function when x is -2. X is -1, go a little bit farther back. When x is -2, something weird happens. There is no value to the function. There's actually like a little blip, this is why we call it a hole in the function. Because when x is -2, the function can't exist. You try plugging a -2 into that. I'll show you. You do not get an answer. There is what's called a hole in the function. Now, the problem with the hole is that you're not going to see it if you just ask Desmos to look at the whole graph. You have to know it's there in order to find it, which is a little bit frustrating, to have to only be able to see something if you know that it's there. So one thing that's a good idea if you ever see a function and you have to analyze it, it might be a good idea just to quickly kind of like drag your cursor around and see if you notice like that little blip. You can see that little, like, oh wait, it just disappeared for a second. And so that is what I mean by being left with a hole. How do you know the y value of that hole? Well, it's not that hard. We know the x value. It's at x equals -2. You find the y value by plugging in the x value, not into the original equation or the original function, because we get 0 over 0, right? If I plug a -2 in there, I get 0 over 0. That's not going to help. But if I plug it into the simplified fraction, plug it into this version, so 2 minus 3 is -1, and sorry, -2 minus 3 is -5, and -2 minus 5 is -7. So the y value in this case would be -5 over -7, or 5/7. And if we look back at our graph, I know that 5/7 is kind of an ugly number, but if we look here, 5/7 is a little bit more than 3/4, sorry, a little bit less than 3/4. And so that's why you can see we're just a little bit less than 0.75 when our number disappears. So at least it kind of checks out. I know 5/7 is ugly, but it is in the right spot. In the next video, I will walk through the process for graphing one of these things from start to finish.